Hey everybody, here we go. Chapter 11. I'm going to prove fundamental theorem for finite abelian groups. I hope. It's going to be in as a series of 4 lemmas. I'm only going to prove the first 2. The last 2 lemmas, I'm going to leave them up to you. Okay, I'm not going to reread what the fundamental theorem says, but basically all finite abelian groups are a direct product of cyclic groups. All right. First of all, if we take the order of the group and pull out all of its prime factors for a specific prime number, p to the n, then we can rewrite the group as an internal direct product of all elements in G whose orders are a power of that prime, okay, and then everybody else. Moreover, we're going to show that subgroup X of all the elements with orders that are p to the whatever, that's actually equal to the prime, the factor of the prime factorization that collects all the primes p. Okay. Lemma 2 says that if you have a prime power abelian group, which is what this H is, then it's a cyclic group times some other subgroup. And so basically we can do induction on can do an inductive argument by just redoing lemma 2 over and over again to show that any prime power order abelian group is a direct product of cyclic groups. And number 4 is just talking about, what if there's some way to rewrite the direct product uniquely, and there is if you just sort of think of a way. It's I don't have it written here, but if you look in the textbook, they've got what it actually means. Okay, let's prove lemma 1. All right, so of course G has order p to the n and m, and H is some set given by all elements in G with the property that x to the p to the n is equal to the identity. K is anything that is in G that doesn't have that quality, basically. It's, must be that. All right, so we're going to, I'm just going to say that H and K are subgroups. You can use the 2-step criterion pretty easily to show that they are subgroups of G. Okay, so to show that G is some internal direct product of those, first I want to show that HK, that product subset or set, is actually equal to all of G. So let's take an element in G, all right, and then, right, notice that the greatest common divisor between p to the n and m is 1. So there are numbers s and t, so that the linear combination of p to the n and m with those factors or those coefficients will add up to 1. All right, so this means that x to the 1 is equal to x to the p to the n times s times x to the m t. G is abelian, so I can switch these guys around. Turns out that x to the m, if you raise it to the power p to the n, you get the identity, right? Because p to the n times m is the order of the group. And all elements have order that divides the order of the group by Lagrange's theorem. So this means that x to the mt must be in H. And likewise, x to the p in S is in K. All right. So that did that bit, right? So this is saying that G is a subset of H times K, but certainly H times K is a subset of G. So we know they're equal. All right. Part 2 of our argument here is to show that the intersection of these guys is the identity. Well, notice that if y is in the intersection, that means that y to the p to the n is equal to y to the m is equal to the identity. Okay? So in other words, the order of y divides p to the n and the order of y divides m, but the greatest common divisor of those things is 1. Okay? So the greatest common divisor of p to the n and m is 1. So y, the order of y is a common divisor, means that it's got to be a divisor of the greatest common divisor, but that's okay. And here's the moreover part. So notice that Theorem 9.5 implies that any abelian group with order p prime to power times m, or must contain an element of order p. Okay. So suppose the order of H is not equal to p to the n, right? That would mean that the order of K, right, sorry, P would be a divisor of the order of K. Which would mean, by that theorem, K would have to have an element of order P. But it doesn't. Okay. Every element in K has order that divides the number m, right? Which has no divisor P, right? So this is by the way K is created, right? What the definition of K. All right, so that's lemma 1. Now, lemma 2, it's kind of, proof of lemma 2 is a little bit long, right? So bear with me. Here, right, the order of G is just a prime power, okay? And we're going to induct on that power. Well, if n is 1, then G is cyclic itself, right? So I don't need to worry about it. You know, you could do cyclic subgroup generated by any element that is not the identity, and that would be our, so G would be this product, internal direct product, right? So that's pretty obvious. So now assume, so suppose all groups that have prime order, all abelian groups of order p to the k for k less than n satisfy the conclusion of the lemma. Okay. And let's assume that G has order p to the n, right? All right. Then take an element A in G of max order. Certainly, if the order of A is p to the n, then we're done. Okay, so if not, then the order of A is p to the m for some m less than n. Okay, and take B to be an element not in the subgroup generated by A with minimum order. Okay. Notice then that B to the P would have to be in A, since the order of B to the P would be the order of B divided by P, and that's less than the order of B. And the order of B was minimal. Okay? So B to the P is a power of A. Now, since A was of max order, right? In G is P to the M, right? Every element has, in G, has order that divides P to the M. All right, so that's true for B as well. B to the P to the M is B to the P to the P to the M minus 1, which is A to the I to the P to the M minus 1. That's the identity, right? Which means the order of A to the I is less than P, or less than or equal to P to the M minus 1. That means that AI does not generate the subgroup generated by A, right? Okay, so there's a theorem from the cyclic group chapter, theorem 4.2, and its corollary 2 implies then that the GCD of p to the m and I can't be 1, right? Otherwise, a to the I would generate the subgroup generated by A. So this means that P must divide I, because the only divisors of P to the M are P to the something, right? So I is P times J for some J. Okay? So let's put it all together. B to the P is A to the I, which is A to the PJ. Okay? Now consider something completely different. Sort of C, which is A to the minus JB. Then C to the P, it turns out, is B to the negative P, B to the P. So C to the P is A to the negative JP. Notice I can distribute the powers, right? Because it's abelian. B to the P. That the negative JP is A to the negative PJ. That's B to the negative P. So this is the identity, which means the order of C must be P, since it can't be 1, right? It's got to be a divisor of P, but since C, oh, sorry, I didn't say this. So the order of C is equal to 1 or P, right? Okay, but B is not in there, which implies that C is not in there, right? If C were in the subgroup generated by A, then that would mean B would be a power of A, which we know is not true. Okay, so then C is not in there, which means C can't be the identity, so that means the order of C is P. Okay, now the order of B is at least P, because it's not the identity, but it has to be smaller than or equal to P, since it's minimal, right? So P is less than or equal to the order of B, which is less than or equal to the order of C, which is less than or equal to P. So that means the order of B is P. You're like, I don't care. So why is that interesting? Well, that means every non-identity element in the subgroup generated by B generates the subgroup. Okay? So this means that the intersection between subgroup generated by A and the subgroup generated by B, right, must be the identity. Else we would have a non-identity element in A and B that generates the subgroup generated by B. In other words, B would be in the would be a power of A again. So we know that that can't be true. Okay. So that's pretty cool. All right. So now we need to show that that there is a subgroup K and a subgroup, this subgroup A here, that actually makes the group G. So I want to show that G is equal to A cross some times K, for some K, all right? To do this, let's consider the factor group G mod subgroup generated by B. Okay. Since G is abelian, all subgroups are normal. So this is a group. Let's use some notation. X bar is going to be the factor group. The factor group representative in G bar element given by the coset of X. Okay. So then we see that A bar must have maximum order in G bar, and this would be because else A bar to the P to the M minus 1 would be in the identity in the factor group, right? That's the identity in the factor group. We know then that means A to the P M minus 1, right, would have to be in the subgroup generated by B. We know it's also in the subgroup generated by A, but that's the identity, okay? And that is a contradiction to the fact that the order of A is P to the M. Okay? So I'm running out of space here, but turns out that K is going to be the pullback of K bar. So, oops, wait, sorry. I didn't say what K bar was. Oh, yeah, so this means, so A bar is of max order. So by induction hypothesis, right, G bar, which is an abelian group with order less than P to the N, right, has to be of the form that and that, okay? So the K that we're going to be interested in is going to be the pullback of K bar, where the pullback under the natural projection homomorphism from G to G bar. So let me say, now notice this must be the identity, and the reason for that is because anything in since any X bar in the subgroup generated by A, any X in here would be give a coset in G bar that's in the subgroup generated by A bar and K bar, but we know that's the identity bar, okay? that is B. All right, but if X is in the subgroup generated by A and B, then it's in the intersection, which we know is the identity. Okay, so that shows that much. To show that G is equal to A times K here, notice that the order of G is equal to the order of this multiplication, or these two, this product of groups, subgroups, because that's the order of A times the order of K divided by the intersection, which we know is trivial. So the natural projection from G to G bar is a p-to-1 mapping. So this is just that, okay, divided by 1. And that's just the order of G bar times P, which we know is the order of G. Okay? So this means G is the internal direct product of these two subgroups. That's what we needed to show. All right, the other two proofs I'm going to leave to you. This is kind of weird, but I ran out of space. But that is the end. Thank you for listening. Bye.